we start to really dig into our study of calculus, we have to always start with limits. Limits are the building blocks. All of calculus is based on limits. There are two areas, two branches of calculus. There is differential calculus and there is integral calculus. And that will be, those two ideas are what we'll spend most of our time on. But both of these, it's all based on limits. All right, and they depend on limits to exist, so we always start, every calculus book will start with usually chapter 1, limits. Now I looked up on Wikipedia what's the definition of a limit, just so I can show it to you and then we can forget about it. This is called the epsilon delta version. Those are epsilon and delta, lowercase Greek letters. And here is the definition. The dependent expression f of x approaches the value L as the variable x approaches the value of c if x, blah, blah, blah. I'm already bored with it. This is something that you're going to understand, but the wording, this is one where the textbook definition is just too much. It's not worth our time to worry about. So as of now, you just need to know both branches of calculus are dependent on limits. Now here's what that thing said, basically. The limit of a function is the height of a function as we get closer and closer to a given x value. I'm going to go ahead and start with the big fact down here. 99% of limits are just the y value. Meaning, this graph goes through a bunch of xy points. That's what a graph is, a bunch of xy points. When x is, for instance, -3, y is 1. When x is 0, y is 2. I'm just picking some nice points. When x is 2, I get some value 2 point something, but I'm just focusing on the good points for a moment. When x is 5, y is 3, and so on. So most of the time, finding a limit would just be finding the y value by subbing in the x value. Unfortunately for us, 99% of limits would be found that way, but 99% of limit problems in your textbook will not work that way because those problems aren't interesting or challenging. So we're going to do a lot more difficult ones, or at least more complicated. But just realize that most of the time a limit is just the height of the function. The limit, and here's some notation. LIM for limit, and a given x value will be written underneath the LIM. So let's say as x approaches -3, the limit as x approaches -3 of f of x. That is how you would say this expression, limit as x approaches -3 of f of x equals. Now, if we're looking at a just normal graph, this graph is undefined to the left of -4, but other than that, it's a normal smooth curve, nothing too weird going on. It goes through the point -3, -3, 1. So the limit as x goes to -3, as x approaches -3 of f of x equals 1. Nothing crazy. It's just the value, all right? It's the height or the value of the function as we get closer and closer to -3. So we're moving our way up this graph this way, we're moving our way down this graph this way. What height are those arrows zooming in on? Basically is what's going on. Another example over here, the limit as x approaches 5 of f of x would equal, make sure you know what I'm getting ready to write here, look at the graph, look at my table, and got it, 3. Okay, so almost all limits on just a typical graph would be just the y value. Not always. Let's see how it's sometimes not. All right, so here's a graph. We have a rational function. These are the functions that sometimes have asymptotes and holes, and you learned about them in pre-cal, definitely, maybe algebra 2. Here's a big fact. So basically this graph is the line. If we were to factor out the top and bottom, cancel the x minus 1s. All right, when you located holes in graphs, you did that. This red graph is the same as the graph of f of x equals x plus 1. It just has a hole in it. The only difference between the graph of this function and this function is the original one, f of x, has a hole in it. So our big fact is this. It doesn't matter what the function's value at 1 is, only the value as you approach 1. So now I'll kind of try to tell you what that means. As we move down this graph from the right, moving our way down, what height are we approaching? What height are we approaching? We are getting closer and closer to this value of 2. As we move our way up this graph, we're getting closer and closer to a value of 2. The graph itself, the function itself, might be undefined at x equals 1. All right, you cannot sub x equals 1 into this function because you get 0 over 0, which is undefined. All right, that's called indeterminate form, and we'll talk more about that soon. But my point is, I do not care that there's an open circle in my graph. The location, the height of that open circle, where my two graphs, my two purple arrows are approaching, that is the limit. So I would say in this case, the limit as x approaches 1 of f of x equals 2. Okay? The height of this graph is 2 at the x value in question. As I approach this x value, my two arrows would run into each other at 2 just before they met. It's like, where would your lines meet just before they got to that open circle? Okay, so here's another version of that same graph. I just kind of made up my own version where I said, okay, everywhere else besides 1, it's that same function that we just learned about. At 1, I'm going to say, okay, I'm going to let that function be valued at 1 there. So I've just added a little dashed line and said, okay, the value f of 1 equals 1. Everywhere else, it's the same as it was on our last slide. Okay? The fact here is you don't change the limit by defining the function at another y value. I don't care if it's defined at all, if it's defined where the open circle is, if it's defined somewhere else. It is completely irrelevant where that dot is. The limit as x approaches 1 of f of x still equals 2. This is the limit no matter whether I add a dot here, I could have added a dot up here, I could have completely left it out. You know, I'm not going to have both of those dots at the same time, but my point being, it doesn't matter where that dot went, it does not affect the limit. All right? The function could be defined anywhere or undefined. And I kind of got that in my last big fact. I'm going to leave it. I'm not going to have a new big fact, but just add to that. It doesn't matter what the value of f of 1, and I'm using 1 in this case because I'm approaching 1. It doesn't matter what the value is or if it is even defined. Okay? When we're looking at limits graphically, I only care about where is the height. Where are these two arrows going to run into each other if they in fact do run into each other. All right, I don't care if it's an open circle, defined somewhere else, not defined at all. Limit is still 2. The height is still 2 as I approach x equals 1. Okay, so here's a big common graph that you always see when you're talking about limits. Remember I said 99% of the time you just sub in. So when we write calculus books, we have to be creative in ways to find graphs that aren't part of those 99%. So this is one of the 1%. And you will see a graph like this in almost all calculus books. What I do by putting an absolute value over top of x minus 3 is when my x values are above 3, so when I am at 3 or to the right of 3, I just get 1, because when x is bigger than 3, those absolute values are meaningless. When I sub the number 5 into the top of this equation, I get positive 2. And I get positive 2 on the bottom, and 2 over 2 is 1. The reason the absolute values make a difference is to the left of 3. When I sub in a number like 2, on the top I get 2 minus 3 is negative 1, and then I absolute value that and get, let me write that down, g of 2 is the absolute value of 2 minus 3 over 2 minus 3. And that's positive on the top because absolute values are always positive, and it's negative on the bottom. So what happens at 3 is I make this jump, and we use the term jump. I make this jump from plus 1 to minus 1, or if I'm moving left to right from minus 1 to plus 1. So there's nothing magical about this graph. It's just one of those 1% graphs that is interesting to discuss when you're talking about limits. So here's the fact. Or let me give you the answer first, and then I'll go back to the fact. What I would say here is the limit, and I changed the name of my function to g of x, as x approaches 3, does not exist. All right, and you can write on your practice problems D and E, and we'll all know that that means does not exist. If I'm coming in from the left and I'm coming in from the right, and these two arrows are not getting ready to bump into each other, then the limit does not exist. So limits don't exist at jumps. And in a future video, we'll talk about left and right one-sided limits, but right now we're just talking about the limit. The limit of g does not exist at 3. Now, the limit of g as x approaches any other number is the value of that number. As x approaches 7, I'm right over here. I'm going through the point 7, 1, so my limit is just 1. The height of this function at 7 is 1, because there's no funny business going on at 1. But at the jump, the limit does not exist. Big fact, limits don't exist at jumps. A floor or greatest integer function is just another example that you'll see a lot when you're discussing limits. There's also a ceiling or least integer function that's just kind of a version of this. But what a floor function does is it always rounds a number down. It rounds it down to the next integer, the next greatest integer that is no bigger than it. So if x is 1.1, or excuse me, if x is 0.1, it rounds it down to 0. If x is 0.8, it rounds it down to 0. If x is 1.1, it rounds it down to 1. It always just rounds down to the nearest whole number. So what I get is a line that just cruises right along here until I get to 1. If I sub in 1, it's going to give me 1. I don't have anywhere to round down, but 1, 1 is here, which means I have an open circle here, and it repeats that process. All right, so these are called step functions or greatest to least integer functions. And again, there's nothing really magical about this. They're kind of interesting. If you are, I don't know if you're talking about, I don't know if you have cell phone minutes anymore, but if you make a call that's 2.1 minutes, you probably get charged for 3 minutes. That would be an example of a ceiling function. But it's just a function that shows up a lot in limit discussions because you have these jumps. Okay, the limit as x approaches 3 of f of x does not exist. I just don't want you to see these and think it's something crazy. It's just another interesting function that lets us get jumps in a graph. It's kind of hard to make those. Most graphs don't have those jumps, but here's an example of one that does. All right, so this is a typical looking question. I've got just a crazy graph drawn. There's probably no function that will make a graph that looks like this, but you'll get a lot of questions that look like this. All right, this is what it's about, finding limits graphically. So I'm going to go through all these points. I've got 7 x values. So we can kind of wrap this discussion up about finding limits graphically. So what I'd like for you to do is pause and see if you can come up with these 7 purple answers. And then when I tell them to you, you can confirm or make a correction if you have any misconceptions. I'm going to start with -7. As I approach -7, all right, as my graph comes in from the left and comes in from the right, where are those arrows getting ready to run into each other? They would run into each other at 2. I do not care that there's an open circle there. I don't care if it's defined anywhere. It happens to be defined up here, but that's irrelevant. It only matters where the arrows would bump into each other if they did. All right, they're not going to make that jump up. It's just the height as we approach -7. All right, -5 is kind of this funky little point, but nothing really strange is going on here limit-wise. Both of my, the height of my function is 0, so my limit is 0. That sharp point will have implications when we start talking about derivatives or differential calculus, but right now it doesn't mean anything. The height of our graph at -5 is 0. Okay, so now we have an asymptote at -3. At -3, coming from the left and from the right, both of the sides of the graph are going up towards infinity. So what we're going to do there is just say infinity. Now technically this is a does not exist because infinity is not a real number, but we are going to be more descriptive. It's more informative for me to say infinity because then it describes to whoever's listening to me, it describes that these two graphs are going upwards towards a vertical asymptote. If I just say does not exist, then that could mean a lot of different things. But infinity pretty much means vertical asymptote, both sides going upwards. Okay, we move over to x equals 0. At 0, here right on my y-axis, all right, as I follow my red line down, what's the height of my graph approaching? All right, my height is approaching 2. That's my limit. I don't care that that's an open circle. Completely irrelevant. All right, it's not defined anywhere else. It doesn't need to be defined anywhere else. My limit is 2. I only care what happens as I approach 0, not when I get to 0. All right, so x approaches 2 is my next one. Now here's a jump. As I approach 2 from the left, my height is approaching 1 right here. I'm on the level of 1. But on the other side of x equals 2, I'm down here at -2. I have a jump, so I have a D and E. Does not exist. Limits don't exist at jumps. Okay, the limit as x approaches 4. So I have another vertical asymptote, but this time one of my functions, or one of my sides of my function is going down to -infinity. The other one is going up to +infinity. In this case, does not exist. I don't have any other more descriptive way to say that, just does not exist. And then finally, at x is 6, I just have a nice normal situation. The function is defined. I put a dot to kind of show that it is right at 4, height of 4, but this is just your typical 99% of the time. But like I said, probably only 1% of your problems will be this typical kind of graph, because why discuss them other than that? All right, so just to kind of sum up that infinite limits discussion. The limit of this is infinity. The limit of this, we'll say -infinity, and this does not exist. All right, so that's a kind of a different topic called infinite limits, but that's, when we're talking graphically, same idea. If they match, technically they're all does not exist, but what your answer should be is infinity or -infinity if they're both going up or both going down. So that's going to wrap up our discussion on finding limits graphically. Make sure you get this. It's a huge building block for our study of calculus.